We will now discuss Class C power amplifier, and this will be divided in 2 lectures. So today is the first lecture in which we will see the circuit, and we will try to derive the expression for the voltage and currents involved with this circuit. And in the part 2 of lecture on this power amplifier, we will try to find out the drain efficiency and output power capability of this power amplifier. So first we will see the circuit of this power amplifier. So this power amplifier uses a single MOS, which acts as switch. And in the load network, we have a series LC circuit. And there is a shunt capacitor C1 between drain and source of the MOS. And as usual, we have RFC here. So this is a Class C power amplifier circuit, and in this circuit, the MOS acts as a switch. So we have seen that switch-based power amplifier, ideally, for example, Class D, has 100% efficiency because ideal switch does not consume any power. And since MOS is intended to act as a switch, so this input voltage is a square wave of obviously large amplitude. Here in this circuit, we see a shunt capacitor C1. So C1 is small capacitor which includes the parasitic capacitors of MOS and RFC. So it includes drain to bulk capacitor of MOS and the parasitic capacitor of the RFC. Since it is small, so typically at very high frequency, we need not even include any external capacitor C1. These parasitic capacitors, they might be enough to play the role of C1. And regarding the inductor, which appears in series with C0 in the load network, this inductor L can be interpreted as sum of 2 inductors. And why we are representing this as a sum of 2 inductors? Such that at the operating frequency, what happens is the reactance of the capacitor gets cancelled out by this L naught, or part of this inductor L. So leading to the operating frequency given by L naught C naught. So this is what happens at the operating frequency, and at the resonance of LC naught, we will have this condition. So this implies omega S resonance is going to be 1 by square root L C naught, and this then can be written as L1 plus L naught C naught. So now we see that this resonance frequency is going to be smaller than the operating frequency. So since C naught gets cancelled out by part of the inductor L, so at the operating frequency, we can represent the class E amplifier equivalently as at the operating frequency in this fashion. So C1 of course will be there, but then L0 portion of L gets cancelled out, and we have zero impedance for L0 and C0, and then we have our load here. Since in this circuit MOS acts as a switch, so the final equivalent circuit would be like this. That we have here the RFC, and then C1, and then MOS as a switch. And then we have here inductor, and finally the load. So this is the final equivalent circuit of the class E, which we will analyze. Now here we can see that there are going to be various waveforms for the current and voltages. So first is going to be well known DC current, which will be flowing through RFC, and then of course current I1, which will be of sinusoidal nature, and then these two currents, they will combine here to produce total current I. And since switch will be closed for one half of the input and open for the other half, so this current will actually get divided into these two parts through the switch, which we will be calling IS, and through this capacitor IC1. So these are the various currents involved in this circuit, and there will be one voltage involved, switch voltage, which will also be the voltage across the capacitor C1. And all of these are going to be time dependent, except of course the IDC. So this is the drain node. So at the drain, the KCL implies IDC, which is going to be DC current, plus I1, which is going to be time dependent, equal to I switch current plus IC1 current. And at any given moment of time, of course, only one of these two will be present, other will be zero. Because when switch is closed, IS will be there and there will be no current through capacitor. When switch is open, no current through switch, but current through the capacitor C1. And here additionally, okay, let me write this. This is the DC current, and I1 is going to be sinusoidal. So in general, it will have certain phase at t is equal to 0, initial phase. More compactly, we will be writing these equations in these forms, where theta is equal to omega t. So this I1 is sinusoidal, and since I1 gets added with IDC to produce the total current, which gets divided between switch and the capacitor. So these switch and capacitor currents, they are going to be basically part of offsetted sinusoidal current. So our ultimate goal, of course, is to find out the efficiency and output power capability of Class C power amplifier. But for that, we need to actually know the waveforms for these quantities, particularly the switch voltage. This is going to be the most important waveform which we will be needing. So there are certain assumptions that we will be making here for the analysis. So well known is that RFC is large inductor, implying constant current through it. That means this is DC current. And MOS acts as ideal switch. And in this analysis, we will conclude from this ideal switch behavior that no on resistance offered by MOS. So this is the simplifying analysis. Otherwise, it will be pointed out that this class E circuit basically tries to tackle the loss of power resulting because of on resistance of MOS. So this will be elaborated shortly, but including that resistance will make the efficiency and output power capability calculation a bit more involved. So we are going to overlook. The third assumption, which is going to be very important, and actually it allows us to take the current through the load network and the load of sinusoidal form, is that the loaded Q of this inductor or inductor L or C naught is large enough to suppress higher harmonic current for the load. So we will see that why this assumption is important. And by the way, the loaded quality factor of series LC naught circuit is going to be given by omega L by RL or 1 by omega C naught RL. So we are talking about loaded because we have external resistor RL. Otherwise, if RL represents the loss of inductor or capacitor, then it would be simply the quality factor of the series circuit. Loaded, sorry, here I forgot to write quality factor Q of the inductor or C is large enough to suppress higher harmonic currents. Okay, so in this assumptions, we are not going to take the resistance offered by MOS in the on state. But as was pointed out, this class C amplifier basically tries to tackle this loss resulting from this R on resistance. So what happens? Suppose we have this MOS here and there is a shunt capacitor. So invariably this C1 will be there even if we do not connect any external C because of CDB and because of RFC parasitics. So invariably there will be a capacitor, and if you want to operate this MOS as a switch, then we will have this scenario. And let us briefly include the resistance, small resistance offered by this MOS in the on state. So the equivalent circuit now is going to be like this. So suppose this switch closes, and at that moment when the switch closes, there is a small charge and certain voltage on this capacitor. So now there is a low resistance path through this switch. So what will happen is this capacitor will start getting discharged through this switch, that means through MOS, and because of this R-on, there will be power dissipation and heat will be developed in this R-on. So this implies that there will be power dissipation in the MOS in on state. So because of this, the efficiency of the circuit where this MOS is being used as a switch will be low. So what this class C power amplifier basically tries to do is that it tries to ensure that there is no voltage across C1 when the switch closes. So when the switch closes and there is no voltage or there is no net charge on this capacitor, there will be no discharge current. So there will be no heat generation in this MOS. So if that happens, then of course the efficiency is going to be higher. So class C amplifier basically does this thing to ensure that a real life switch based power amplifier offers high efficiency. Now what we will be trying to do is the first objective is going to find out the switch voltage which we have is pointed out here, and it is this voltage which is going to play important role in all the analysis. So finding the switch, or this is also going to be capacitor C1 voltage Vs theta. So this is what we will be aiming. Once we know this, we will be able to find out the load power, DC power, and efficiency and output power capabilities. Now the starting point is going to be this current, the fundamental current that we have assumed through the load network. So load current we have assumed to be this sine theta plus phi, where Pi is the initial phase, IP is the amplitude. Now the total current I1, sorry, I is IDC plus I1. So this is IDC plus IP sine theta plus phi. Now this current gets splitted between the MOS or the switch and C1. So a part of this will be flowing through switch when it is closed, and the other part or the other half will be flowing through capacitor when the switch is open. So that is what is going to happen here. So now using this current, we have to find out the voltage waveform, and then we can complete the rest of the analysis. So before we try to find out the voltage waveform, we will have a look at the various waveforms qualitatively, and then try to derive the voltage waveform. And we can note that since we have three unknowns here, IDC, the amplitude of the fundamental, and the initial phase, so that will also possibly contain these three unknowns, and we will have to ultimately find out these in terms of the known quantities, specifically the supply voltage VDD. So we are now going to draw the various waveforms. The first waveform is, of course, going to be the input voltage, because this decides when the switch closes and when the switch is off. And as was pointed out, this is going to be basically a square wave. So switch is going to be on for this portion, and it is going to be off for the second part. Now the most well-known form of the current is going to be this DC current, which will be flowing through the RFC, and it will have certain constant value. Now we have assumed a sinusoidal current through the load with certain offset. So here we have a small page at t is equal to 0. Now the total current is actually going to be sum of this waveform and this, the DC current and this sinusoidal. And here we will have the amplitude IP. So now we are going to draw the total current, which gets divided between the switch and the capacitor. So this is basically offsetted sinusoid. So this is going to be the waveform for total current. Now we have seen that this portion is the duration over which the switch is going to be on, and for the rest of the cycle, this is going to be off. So when the switch is on, it offers least impedance path. That means the total current must now be flowing through the switch. So the switch current is going to be like this. And at this moment, switch turns off. So the current is going to be 0 for one complete cycle. And then again a part of sinusoidal current like this. So this is going to be the switch current. And the remaining part of the total current is going to be the capacitor current, C1 current. So it is going to be 0 for the first half, and then it is going to be positive, and then negative, and then 0, like this. So here we see that the capacitor current is positive for certain portion and negative for the rest of the part of the second half of the complete cycle. So here we see that for T1 duration, the current flows into the capacitor, and for this T2 duration, the current flows out of the capacitor. The current flows out of the capacitor for T2 duration. So what will happen is capacitor will be getting charged during T1, and capacitor will be getting discharged during T2. So voltage will increase. So Vs will increase over this portion, and Vs will decrease over this portion. So now we can qualitatively draw the V switch or V capacitor voltage waveform. So there is a no current through the capacitor over the first half, so voltage is going to be 0, and then the voltage will start increasing starting from 0 like this up to this moment, and then it will decrease. So this is going to be the voltage waveform. So what we have shown here is the waveform that actually we will be studying or analyzing, but there are certain variations of this waveform possible. For example, what we have shown here is a switch voltage to be equal to 0 at 2 pi. So Vs 2 pi is equal to 0, and it remains 0 afterwards also, of course. Not only that, you can see that it gradually becomes 0, and so sort of derivative is also equal to 0. But now if you look this waveform from derivative point of view, then there are various possibilities. For example, this waveform could have been like this. That is, of course, it is 0 for this portion, and voltage increases, and then it decreases, but then with 0 attaining at 2 pi. But now here what we have is slope also. So dVs by d theta here is negative. So this is one possibility for Vs. Then second possibility is that it discharges very quickly. Here it charges up to this point and discharges and then starts charging. So again, maintaining zero voltage at 2 pi, but now you can see that the derivative is greater than zero. But we are going to consider the case when derivative is going to be zero. So this gives rise to the optimal case of class E, but each of these cases also represent class E. So we are going to study this case 1, or case 2, and case 3 will be neglected. And maintaining switch voltage equal to zero at this moment uh, is required to eliminate any power dissipation in the MOS when the switch closes. So this first condition is very important for the higher efficiency of the class E circuit. So now we have all these waveforms. So what we can do is we can write the expression for these currents, and we see that it is this capacitor current which is responsible for this capacitor or switch voltage. So we need the expression for this IC1 so that we can find out ds theta. So we will now first try to write these expressions for the current and then find out the voltage. This switch current and capacitor current, they are the part of total current. So total current we have already seen is IDC plus IP sine theta plus phi. So therefore, the switch current is equal to IDC plus IP sine theta plus phi, and this happens over the duration 0 to pi. That means for the first half. And then, of course, it is 0 because switch is open now for this duration. While the capacitor current is 0 during the first part, but it is equal to the total current for the second half. Now we are going to use this switch current to find out the capacitor voltage. So we know that switch current IC1 theta, or let me write it in terms of time, is going to be C1 d switch by dt. So here we can write this as d Vs omega t by d omega t IC1 omega t. So in terms of theta, we can write IC1 theta is equal to omega C1 dVs theta d theta. So this says that d Vs theta is equal to 1 by omega C1 IC1 theta d theta. So now we can integrate this equation to find out the voltage. So since here the current starts flowing into capacitor at t is equal to pi, or theta is equal to pi, so we integrate from theta pi to certain theta. So on the left hand side, we get switch voltage at certain theta minus switch voltage at pi equal to 1 by omega C1. And now we can substitute expression for IC1 over this portion, which is IDC plus IP sine theta plus phi d theta. So we can now integrate this. This is from pi to theta I dc d theta plus ip integral pi to theta sine theta plus phi d theta. So this gives omega c1, and here we get idc theta minus pi, and when we complete the integration of this second one, minus ip cos theta plus phi plus cos phi. So this is what we will get when we complete the integration. So now on the left hand side, we have two terms, Vs theta, which we want, and Vs at pi. So we can see that Vs at pi is going to be 0 here. So the second term on the left hand side becomes 0, and what we have is only Vs theta is equal to so this is the going to be the voltage across the capacitor, and here we can see that we have unknowns IDC, IP, and initial phase phi. So we have three unknowns, and we need three equations to determine them. But before we try to find out this, we would like to return back to the assumption that Q should be large, the loaded Q should be large, so that sinusoidal current flows through the load network. So we have seen that this Vs is going to be of this form. So this is a periodic waveform, 0 for the one half and non-zero for the other half. So we see that in general, this Vs will contain various harmonics. So if we do the Fourier expansion, so we will have a DC component and various harmonics. Where phi n is going to be the initial phase of nth harmonic, and Vn is the amplitude. So what happens here is equivalently in this circuit that we can say that we have this network, and this is sort of getting excited by this Vs theta, where theta is omega t. So what will happen here is that there will be current, you can say that, excited by each of these harmonics into this network. Say In. So In is nth harmonic current through RLC naught. So now if you see that what will be In, so this will be equal to the nth harmonic voltage divided by impedance of the load network for nth harmonic. So this impedance is for nth harmonic, we know that is going to be Jn omega L minus 1 by J n omega C naught plus RL. So here we see that these two, or the imaginary part, is going to get affected by the harmonic. So now we can see that what will be the current because of various harmonics. In fact, now we can write this impedance in terms of the quality factor. So we can take RL common and we can take RL first. So this is 1 plus J n omega L by RL minus 1 by n omega C naught RL. And this becomes 1 plus J n into Q, the loaded Q, minus 1 by n Q. So for nth harmonic, this is going to be the scenario. So this is the definition of Q. So now if we want to know the nth harmonic current, we need to divide the nth harmonic amplitude by this nth harmonic impedance. So Vn divided by RL 1 plus J n Q minus 1 by n Q. So here we see that as n increases and goes up, the In comes down for fixed Q. So whatever may be the Q, this is always going to happen. That means the harmonic currents, they are anyway going to reduce. However, for large Q, and now say you fix the harmonic when n is fixed. So here also we see that as this happens, as Q goes up, the In comes down for any value of n, for any fixed value of n. So this term is in fact going to reduce very fast for large Q and for large n. So we can see that In in fact approximately becomes Vn by R into 1 plus J and Q. So if you take Q larger, then nth harmonic contribution is going to be 0. And for n is equal to 1, what we see is I1 is going to be V1 divided by RL into 1 plus J omega L, and L we have represented in this form, omega C naught, like this. So we see that this portion gets cancelled out by omega L naught. So we have RL into 1 plus J omega L1. So here we see that now we have a value omega L1 which is smaller than in general the value that we will be encountering. So we will see that the fundamental is going to be the strongest. So largest current that will be flowing through the RLC network, this network is going to be the fundamental. And if we take sufficiently large Q, in fact, it turns out that if you take Q is equal to greater than 3 or 5, then the higher harmonics, they will be hugely suppressed compared with the fundamental one. So that is why we said that the current that will be flowing through the load network is going to be sinusoidal. So now we return to our intermediate objective of finding out these three unknowns, so that we can find out the expression for the switch voltage in terms of VDD, and then we can find out the various powers and efficiencies and output power capability. And third is, if you recall this circuit, you can see that the drain voltage is always going to be equal to VDD. So here this is so DC voltage is always going to be VDD, and since there is a switch voltage between drain and ground, this Vs, that means the DC of this Vs must be equal to VDD. So this is going to be the third condition that will be used for finding out those unknowns. The DC of V switch is equal to VDD. So these are the three equations which we will be using one by one. So now we try to use the first one. So we substitute this in the expression for the voltage waveform that we derived, and that gives rise to this expression. So this implies IDC into pi minus IP into 2 cos phi is equal to 0. So this gives rise to IP is equal to pi by 2 cos phi IDC. So this is, so we will be calling as equation 2 an important equation which we'll be using, and equation 1 can be taken as the equation for the expression for V switch, which we did not label. So this we will be using later on. But this is not the only way in which we can arrive at this equation. We can look at the current waveforms, the switch and the capacitor current waveforms. Here, these two. So here we see that switch current is never negative. That means there will always be finite DC contained in this switch current. So this is one observation, and when we set up this equation, we will end up to the equation number 2 that we just derived. Another observation is from circuit point of view that we know that there can never be any DC through capacitor, no DC current through capacitor. So that means the capacitor waveform IC1 is of such a nature that if you find out the average over one cycle, it must be equal to 0. And in fact, that is what will be the case. So if we set up equation for the average of IC1 is equal to 0, that will also lead to the same equation that we have derived. So there are basically three ways in which one can derive the relation between IDC and IP. So can be derived from first switch value is equal to IDC, or from the average of IC1 is equal to 0. So these are the other ways in which one can get this equation. Now, with this equation 2, we can rewrite the expression for I switch and I capacitor and the switch voltage. So therefore, this switch current equation becomes IDC into 1 plus pi by 2 cos phi sine theta plus phi for phi and 0 for the rest of the cycle. Similarly, IC1 can also be written. This will be 0, but IDC to 1 plus pi by 2 cos phi sine theta plus phi for the second half. And important one is this switch voltage, which we will be again using 0 for the first half and 1 by omega C1 into IDC theta minus pi. Now this IP gets replaced by pi IDC by 2 cos phi cos theta plus phi plus cos phi. We can do the further simplification. We see that cos phi is here and here. So one can do the further simplification of this. To get the expression like this. 0 for the first half and then IDC by omega C1 into theta minus 3 pi by 2 minus pi by 2 cos phi into cos theta plus phi. So this is going to be for second half. And one can expand this cos theta plus phi to get yet another equation. So we still need to know what is IDC and phi. So now using condition 2 on 3a, that means derivative of switch at 2 pi is also equal to 0. This is also called zero derivative switching condition. So this from 3a will give rise to 1 plus, or in fact 3b, 1 plus pi by 2 sine theta evaluated at 2 pi plus pi by 2 cos theta evaluated at 2 pi into tan phi is equal to 0. So this gets simplified to 1 plus pi by 2 tan phi is equal to 0, implying that tan phi is equal to minus 2 by pi. And if we solve for this phi, this phi turns out to be minus 32.48 degree, or equal to minus 0.57 radian. So this is the value that we have for our case. From this tan phi, we can find out cos phi, because we can see that this cos phi appears in the expression for switch voltage. So we can find out cos phi, and this will turn out to be pi by square root pi square plus 4. And since tan is negative, so sin phi is going to be negative, and it will be given by this value. So with this, we can rewrite the expression for the current and voltage waveform that will get modified. So we can write the expression only for the total current, because part of this is IS and IC1. So this becomes IDC into 1 plus. So we used to get pi by 2 cos phi, so that becomes pi square plus 4 whole square root divided by 2 sine theta plus phi. So from here we can write value for this. Yeah, so this is what has been used here. And now the switch voltage becomes 0 for the first half, and IDC by omega C1 theta minus 3 pi by 2 minus pi square plus 4 whole square root by 2 cos theta plus phi. Now we need to find out what is IDC. So we use condition 3. So it says DC of Vs is equal to VDD. That means if you find out the average, this will be equal to VDD. Or we can say that 2 pi VDD is equal to 0 to 2 pi Vs theta d theta. And since Vs is non-zero only from pi, so this limit of the integration gets modified to pi to 2 pi. So this becomes pi to 2 pi, and we can write the expression. So we have expanded cos theta plus phi here to get this expression. So now if one carries out this right hand side, this will finally turn out to be equal to 2. This whole thing is 2 pi dc omega c1. So what we see is VDD is equal to IDC by pi omega c1, or IDC is equal to pi omega c1 VDD. So this completes the finding of the third unknown IDC. So IDC has been expressed in terms of VDD, and IP was expressed in terms of IDC. So therefore, IP can also be written in terms of VDD. Since IP was equal to pi by 2 IDC by cos phi, so we can write IP also in terms of VDD as pi by 2, in fact pi square omega C1 VDD by cos phi. So this is another equation that we will be using later on. Or if we replace phi, then IP becomes pi by 2 pi square plus 4 whole square omega C1 VDD. So this is another expression for IP. So now using this IDC in terms of VDD, the final expression for Vs theta is Vs theta is equal to 0, of course, for the first half, and then pi VDD into theta minus 3 pi by 2 minus pi by 2 cos phi cos theta plus phi. And complete current, total current is pi omega C1 VDD into 1 plus pi by 2 cos phi sin theta plus phi. So once we know this expression for V switch, we can go ahead to find out the various powers and the maximum and minimum value of switch voltage and currents, which we'll do in the next class.